Hey guys, Mr. Bowman here. Today's learning objective is in green and we're learning to calculate the rates of change. And this is a skill that heavily relies on our differentiation. So I guess the first question is, what exactly are rates of change? And to explain or introduce this concept, I'm going to use a simple square as an example. So let's have a look at the square. So this square, all the sides are the same, and we're going to say that those sides have an area of, a length of 1 centimeter. So we're going to draw up a table of sides and the resulting area. So if the sides are 1 centimeters, that's going to give us an area of 1 centimeter squared because of base times height. But let's say we've changed the shape. So let's say it's now 2 centimeters. So that means a 2 centimeter side would have a 4 centimeter squared area. And then finally, it's changing again. It's got bigger. So let's say all those sides are 3. So 3 centimeters, that would give an area of 9 centimeters squared. So what we're talking about, rates of change, is as the side changes, what is the corresponding impact or change to the area? So in this case here, that's increased by 3 centimeters squared. And the next one from 2 to 3, that's increased by 5 centimeters squared. So we're trying to mathematically quantify how much is the area changing. So from here to here, that's the first square we have, but we can see there's 1, 2, 3 squares added. And for the next one, that's the 4 we already had, and we got 1, 2, 3, 4, 5 added as well. So we're going to exclusively focus, well, we can do it visually or with a table, but how can we do this using our calculus skills? To explain this, we're going to get into 2 examples, and then we're going to get into heaps of practice as well. So let's change the pen color. Let's use the blue pen for the first example. So what we're doing is we're looking at a water ripple. And if you don't know what a water ripple is, so think of a bit of water dropping into another bit of water. And it initially has a little drop mark. And then very quickly, it has a ripple or a circle around it. And then that ripple moves again and again and again until you've got a series of circles or ripples. And what we're trying to do is we're trying to calculate, well, what is the rate at which the area is changing? So for example, we can find the area of the inner ripple. So what's that area? But what would that be after that? So that would be the next one. And then if we go again, what would it be after that? And then finally, what would it be after that? So we're trying to figure out how much would be changing as the radius changes as well. So we're back in the blue pen. Okay, so we would be comparing, so let's get into our formula actually. So first step, always come up with a formula or an equation. And in our case, we're comparing the area and the radius of the ripple. And we've got a formula, so we're dealing with circles typically. So the area is going to be equal to pi r squared. Okay, and from that, step B, we do need to differentiate. And just a reminder, the derivative or differentiation, that tells us about the change. And that's why it's really important to find when it changes or how much it changes at a particular point. We need to have our derivative, which is an expression for the rate of change. So let's differentiate this. So a dash is going to be equal to 2 pi r. And then step C at the end, we need to substitute. So normally you're trying to find out, well, how much is it changing at a particular point? And in our case, well, we are interested, well, how much is it changing when the radius is at 1.25 centimeters? So let's put that 1.25 in. So A dash is equal to 2 pi times 1.25. If you put that into your calculator, you're going to get 7.85. And I rounded that number to 2 decimal points. And our units, it's an area, so it's a centimeters squared. But we're not finished yet. After that, we need to describe what's changing. So let's get rid of that circle. Let's figure out what's changing. So it is changing at 7.85 centimeters squared per centimeter of the change. So of the change in the radius. So at 1.25, if that radius changes by 1 centimeter, we would expect the area to change by 7.85 centimeters squared. So hopefully you found the first example useful. If you haven't got it down, please pause, get that example down. Any questions or issues, you got to let me know. What I'm going to do now, I'm pausing the video. I'm going to clear our first example, and we're going to get into our second example. Okay, guys, we're back. In white, I've got our second question. So we have been asked to calculate the rate at which the volume, so I'm going to underline that, that's one of the units, the volume of a sphere, so sphere is really important as well, is changing with respect to the radius at the instant where the radius is 15 centimeters. So we'll underline that whole thing. So we've got a whole lot of information. And so what we're going to start off with, like we did for the previous example, we need to form an equation. And in our case, we're trying to compare the volume with the radius. And there's a very well-known formula for that. And that formula, the volume is equal to 4/3 of pi r cubed. Step number 2, we are needed to differentiate. And that will give us an expression for the rate of change. So in our case, V dash, that is going to be 4/3 times 3. So the one up front times the power, times pi r squared. So that power is dropped by 1. And if we simplify that, that's going to be 12/3 times pi r squared, which is equal to 4 pi r squared. So that's our derivative. And the last step, make sure you substitute. You've done all the hard work. You wouldn't want to miss the easy part. So we've been asked about the radius at the 15 centimeter mark in the question. So we're going to substitute that 15 as our radius. So there we go. So we've got 4 pi times 15 squared. If we figure that out, so 15 squared is 225 times pi. All of that becomes 2,827 centimeters cubed. And that is rounded to 1 dp. And just noting, so that's the change of the volume. So we need to be a bit more detailed. That is 2,827 centimeters cubed per millimeter increase in the radius. And that there would wrap up and finish off your answer. So what we're going to do is I'm going to pause the video again, make sure you get this example down. So we've got 2 basic examples down. I'm going to do one more example just to show how we can extend this skill, and then we're going to get into heaps of practice. So we've got our example. I've written it down in yellow, and this does continue on from our initial discussion. So if the square's area changes by 20 centimeters squared, what would the square's dimensions be? So this will be very similar to our previous example. firstly, we need to come up with an equation. So the area is going to be equal to the sides squared. We then need to differentiate. So this hasn't changed from the previous one as well. So the area dash is going to be equal to 2s. And then the last one here, substitute. So this time around, we're not given the area, so the sides or the radius, we're given the change. So what we're going to do is a dash, we know is going to be to 20. So 20 is going to be equal to 2s, which means s is going to be 10. So what that means, coming back to the question, what were the dimensions of the square? B, the square would have sides of 10 centimeters when the area is increasing by 20 centimeters squared. So that wraps up our video. We did 3 examples in the end. Hopefully you found it useful. Now let's get into heaps and heaps and heaps of practice.